So we are going to talk about bivariate distributions. As you can see, the examples or the functions or probability distributions listed from 1 to 6 are all examples of bivariate probability distributions. As the name implies, you have two variables in the probability distribution, x and y, x1 and x2, or any nomenclature that may be used. But you have two variables essentially, two ranges, the range for x, the range also of y. The nature of the range will determine whether the distribution is continuous or discrete. So the first distribution f of x comma y is equal to x plus y is continuous because the range of x and the range of y between 0 and 1 are continuous. The second distribution f of xy is equal to x plus y all over 21 is an example of a discrete probability distribution, joint bivariate distribution, because the range of x and y are discrete. The third example, f of x comma y is equal to k into bracket 2x plus 3y is also a continuous bivariate distribution. Now, the k is a constant. Looking at number 3, 4, 5, the k is a constant and it can be computed when we integrate over the double range, the range of x, the range of y. You integrate this f of xy and equate it to 1 because it is a probability distribution function, or probability density function rather, a joint probability density function. So the double integral over the range of x and y will be equal to 1. When you do this computation, you'll be able to isolate and get the value of k for which f of x comma y will be a true probability density function. So bivariate probability distributions are probability distributions having two random variables, x and y, that may or may not be independent of each other. So independence is a phenomenon that is related to bivariate distributions or multivariate distributions as the case may be. You say two variables are independent if one does not depend on the other. Their covariance is equal to 0, which also implies that uh, the value of its correlation is also equal to 0 because the correlation is a function of the covariance. So with bivariate probability distribution, some common concepts which we will also look at are the conditional distribution, the marginal distribution, the concept of independence, the conditional expectation, marginal expectation, joint expectation, the variance covariance matrix, the correlation, and a few others. So, as I said, a bivariate distribution can either be discrete or continuous. Now, the conditional probability distribution. If you have two random variables x and y, and they have a joint PDF given by f of x comma y, then the conditional distribution of y given x is this: probability of y less than or equal to y, given that x is less than or equal to x. Now, which is also equal to the CDF f of x comma y over the marginal CDF of the random variable x, that is f1 of x. Now the PDF, the conditional PDF of y given x, which is given by f of y given x, is just the f of xy over all over f1 of x, where f1 of x is the marginal PDF, the marginal probability density function of x. f2 of y is also the marginal probability density function of y. So f1, f2, they are all marginal densities. Capital F1, capital F2, they are all marginal cumulative distribution functions. So if x and y are independent, then the PDF f of x comma y is equal to the marginal f1 of x times the marginal of y f2 of y, and the conditional PDF fy given x is just equal to f2 of y. That is, they don't have any connection between themselves, they are independent. So the conditional distribution of two independent random variables is the same as the marginal distribution. So you see the conditional distribution f of y given x is the same as the marginal f2 of y. Let us now look at an example. Example 1. Given that f of x comma y is equal to 4xy, and the range of x is 0 and 1, and the range of y is also 0 and 1. You say you should find the marginal fs given y and fy given x. Then you determine whether the x and y are independent. Now f of x comma y is given by 4sy, 0 less than x less than 1, 0 less than y less than 1. F of x given y will now be given as the joint f of x comma y all over marginal f2 of y. But we can calculate the f2 of y as this. Integrate, because it's a continuous PDF. You integrate over the range of x, that is f of x comma y dx, integrated over the range of x. The range of x is between 0 and 1. This is the range of x, 0 and 1. So that is what we have put here, 0 and 1 for xy dx. When you integrate it and evaluate at x equals 0 and x equal 1, you have 2y as the marginal density of y. That is, f2 of y is equal to 2y. Similarly, because they are symmetric, f1 of x, when you integrate over the range of y, it will also give you 2x. Therefore, f of x given y is just the joint 4xy over 2y, which gives us 2x. And you can see that this 2x is the same thing as the f1 of x. Likewise, f of y given x will also give us 2y, which is the same thing as f2 of y, which implies that x and y are independent. So we have proved independence using the conditional density function of f of s given y and f of y given x to establish independence. If x and y are independent, then the conditional will be equal to the marginal. If they are not independent, the conditional will not be equal to the marginal. Second example, given that f of x comma y is equal to b into bracket x plus 2y, where x ranges from 1 to 3 and y ranges from 0 to 2. Now the question is to calculate the value of b, the constant for which f of x comma y is a bivariate probability distribution. Second question, obtain f1 of x, f2 of y, and use them to determine the conditional fs given y and fy given x. So the solution goes to us. First of all, calculate the constant that makes f of x comma y to be a true joint probability distribution, joint probability density function. And we go about it this way. F of x y dx dy, you can see that the range of x is put first to correspond with dx here, and the range of y is put second to correspond with dy here. Any mixing of the range will not give you the correct result. So you take note, the range of x is 1 and 3. That is what will come here, 1 and 3. And the range of y is 0 and 2. And that is what will come here, 0, 2. So that is what we have here, 1 and 3, 0 and 2. You equate it to 1. Solving, integrating, we get to this. When you integrate, you have x squared over 2 for this first term, then 2xy for the second term. Integrate with respect to x. Then you now evaluate that x is equal to 3 and x is equal to 1. That will give us 9 over 2 plus 6y minus 1 over 2 plus 2y dy. When we can now integrate again and evaluate as y is equal to 0 and y is equal to 2. When that is done, you can see, of course, making sure to equate it to 1. You can see b will be equal to 9 over 2y plus 6y squared over 2 minus half y minus 2y squared over 2 over this range, which can then be resolved to get b is equal to 1 over 16. B is gotten as 1 over 16. So the f of x comma y will now become 1 over 16 into x plus 2y, where x is between 1 and 3 and y is between 0 and 2. Take note of that, between 0 and 2. Y is between 0 and 2. So the marginal f1 of x, you integrate f of xy dy over the range of y, 0 and 2. And that gives us, if it will now resolve to 1 over 8x plus 2 over this range. Similarly, f2 of y is equal to, when you follow the resolution, you follow it the same way, you see it is 1 over 4 into y plus 1, from y going from 0 to 2. Therefore, the conditional density function is f of x comma given y rather is equal to this over this. We divide them appropriately to get 1 over 4 into x plus 2y all over y plus 1. Similarly, fy given x is gotten to be 1 over 2 into x plus 2y all over x plus 2. So you can see that even given the two functions, you can see that they are not independent. You can see that f of x given y contains both x and y, and f of y given x contains both x and y That is an indication of non-independence. That is, they are dependent. Once you have a conditional distribution that contains both x and y, it shows that the two random variables x and y are dependent, not independent. So these are some examples. Determine whether x and y in example 2 above are independent. That we have shown that they are not independent, but you can establish that by multiplying f1 uh, of x. I mean, using the conditional distribution, can it be, is the fx given y, is this equal to f1 of x, and it's f of y given x, is it equal to f2 of y? If that is not the case, then they are not independent. So the conditional expectation is just making use of the conditional PDF that you have obtained in the, for example, this one or this. You can use it to compute the conditional expectation, and it is given by, for a discrete distribution, it is summation over the range of x times the conditional PDF px given y, or fs given y, whichever convention is being, whichever case is being used. That is for the discrete example. Then when the function is continuous, you have an integral x multiplied by f of x given y dx for the continuous case, integrated over the range of x. So similarly, you can also obtain a expected value of y given x. We should take note that the variance is given by this. The variance of x is the expected value of x squared minus the expected value of x all squared. The variance of y similarly, and the covariance is expected value of xy minus expected value of x times expected value of y. The covariance is equal to 0 implies that this is equal to this. The expected value of xy is the same thing as expected value of x times expected value of y. So if that is the case, covariance xy is 0 if and only if x and y are independent. So this is another way of establishing independence. If you are able to compute the covariance and it is equal to 0, that implies that x and y are independent, because the covariance can only be equal to 0 if and only if x and y are independent. So that takes care of that. Now we have the bivariate normal distribution, like the normal distribution with only two variables, x1, x2, or x and y. You have the mean vector mu1 and mu2. That is, mu is the mean vector, x is the variable vector which contains x1 and x2. That is it, x contains x1, x2. And the PDF, the bivariate PDF, is given by this function f of x1 comma x2 is equal to this, where V is the variance covariance matrix of the two variables x1 and x2, where the diagonals of that 2 by 2 matrix contains the variance of x1 and variance of x2 respectively, and the off diagonals is the covariance of x1 and x2. So the off diagonal term are equal, and they represent the covariance of x1 and x2, and it can be represented in terms of the variances. can say sigma 1 squared is the variance of the first variable x1, sigma 2 squared is the variance of the second variable x2. Then rho is the correlation coefficient between x1 and x2, and it's also equal to sigma 1 sigma 2 times rho to get the covariance. V, this is the determinant of the variance covariance matrix, which is equal to sigma 1 squared times sigma 2 squared minus rho squared multiplied by sigma 1 squared times sigma 2 squared, which simplified to be sigma 1 squared times sigma 2 squared into bracket 1 minus rho squared. Of course, we have said rho is the correlation coefficient between x1 and x2, and is sigma 1 2 all over sigma 1 as sigma 2. That is covariance of x1 and x2 divided by the standard deviation of x1 and x2. The joint PDF of the bivariate normal distribution can be expressed in a more compact form. You have uh, where Q is the common term that we use for it, the quadratic form of the normal bivariate normal distribution. The quadratic form is a two is in form of a quadratic function expressed in x1 and s2 in powers of 2. So that f of s1 and s2 can be expressed in that more compact form. Now, covariances. These are identities that can be established easily. The covariance between x and s is equal to the variance of x. That's the first one. The second one, the covariance between x and y is the same thing as the covariance between y and x. And the third is covariance x1 plus x2, y is the same thing as covariance x1y plus covariance x2y. Then the variance of x plus y is the same thing as the variance of x plus 2 covariance of xy plus variance of y. And 5, the covariance of ax, by, where a and b are constants, is equal to ab covariance xy. Let us look at some of the quick proofs. Number 1, covariance of x is the same thing as the square value of x squared using the formula for covariance. The square value of x squared minus the square value of x times the square value of x, which we can see from here is equal to the variance of x. So it's a one line proof. The second one also is a one line. Covariance of xy is the square value of xy minus the square value of x times the square value of y, which is the same thing as just interchanging them. Instead of xy, you write yx minus the square value of y times the square value of x, which is equal to covariance of yx. And the fifth item is covariance ax, by is the square value of ax by minus the square value of ax times the square value of by. When you bring out ab being a constant, you have ab a square value of xy minus ab a square value of x a square value of y, which can also be further factored. You bring out ab and put everything else. The square value of xy minus the square value of x times the square value of y, so that it will now become ab covariance x, y. So we shall this number 3 and number 4 are therefore given as an exercise that should be proved. You provide a proof of it. Very important. For any bivariate probability distribution that is given by f of x, y, we can easily compute the mean vector mu x, mu y, and the variance covariance matrix sigma s squared, sigma sy, then sigma y squared. This is called the variance covariance matrix. And that we can do by computing expected value of x, expected value of y, which will give us the main vector. Then you compute variance x, variance y, covariance xy. Of course, before you can compute expected value of x and expected value of y, you must first of all obtain the marginal probability density function of x and y. You must obtain the marginal. After obtaining the marginal, then you can now proceed to obtain expected value of x and expected value of y, variance of x, variance of y. Then the covariance of xy is obtained from the joint f of is xy multiply the integral of xy multiplied by f of x comma y, the x, the y. You integrate it over the range of x and y to get the expected value of xy, which you will now use to obtain the covariance as well as the correlation if needed. So if you are given a function f of x comma y is equal to x plus y, where s range from 0 to 1 and y is also from 0 to 1, show that the mu, that is the mean vector, is equal to 7 over 12, 7 over 12. The variance covariance matrix is 11 over 144, 11 over 144 minus 1 over 144 minus 1 over 144. You can establish this, as I said, by obtaining all these functions, the f1 of x, f2 of y, which we will now use to obtain the expected value of x, expected value of y, the variance of x, the variance of y. You need all those things from f1 of x and f2 of y. Then the covariance of xy is obtained using the uh, joint PDF. Is expected value of xy, expected value of xy. You use it to obtain the joint PDF, and from there you can now proceed to determine all the necessary components that you need in the computations. So as an assignment, you should compute mu and v, that is the mean vector, and the variance covariance matrix for each of the bivariate distributions, that is number 2 to 6, listed on page 1. For the cases 3, 4, and 5, where a constant k is given first, you should first compute the value of k for which f of sy is a true PDF before going ahead to compute mu and v. So the assignment is to look at, we have done number 1 already, or we have given an hint on how to go about number 1. So you can now proceed with number 2, which is an example of a discrete. So you have summation instead of integration for that one. Number 3 is a continuous. First of all, you have to compute the value of k. Number 4, the same thing, compute k. 5, compute k before you go ahead to do all the necessary computations. As well as 6, also do the needful. 2, 6 is 2 into x plus y minus 2sy over the range 0 to 1, 0 to 1 for x and y respectively. So that concludes our description of the notes, the explanatory note on bivariate probability distributions.